And I studied, my particular mentor there was Alexander Spock, probably not a super famous name, but at the time, there are these different generations of founding fathers and mothers of cystic fibrosis, some of them I've mentioned, and sort of in the modern era, Al Spock and a few others who were professors at different universities were sort of the big names at that time. And one of the interesting things about this, leading up to this, and I can't remember exactly when this is, but probably in the late 70s, Al was a young pediatric pulmonologist and researcher, had done a fair amount of research. And again, at this time, they didn't know what cystic fibrosis was. They just had the description of what the disease was and that it was genetic. And one of the strong going theories for a very long period of time was that there was some kind of a factor made somewhere in your body that circulated around in your bloodstream and could go into different tissues and would actually deter, that then cause cystic fibrosis. So all these people who were trying to make a name for themselves and trying to figure it out were madly researching to find out what this factor might be. And he discovered a factor, I think, either the first or one of the first, turned out to be a false lead eventually, but it was a going theory. So the Spock factor, and I always thought that was a great name. It just rings such an interesting bells. But Al was a wonderful teacher, and interestingly, we had so it was a very small fellowship, small group of fellows, and we have dinner speakers and so on. And Paul de Saint-Denis was still around at that time, and he came down and I think attended our clinic and went out to dinner with us. And he was fairly elderly at the time, but still very distinguished, very, very soft-spoken, quiet, humble type of guy. So I got to meet Paul de Saint-Denis, who reported the hypermegaly dehydration in New York. Okay, so the 80s were big time for CF, and most people here know some of these stories. Some researchers, there's a whole line of researchers, that discovered basically and worked out the whole thing about the electrolyte abnormalities in the epithelial cells, and that was one whole line of research, which initially was separate from the genetic line of research, but then melted after a while. In 1983 was the first CF lung transplant, and this sort of harkens back a little bit to the, because they really hadn't figured this all out yet. There was still some question about whether the CF is in your lungs or CF is somewhere else in your lungs. And I still have people ask me, well, if a lung transplant is done, will the new lungs get CF? Which the answer is no. But when they did this first transplant in 1983, they didn't know the answer to it. And a very brave patient and a very brave doctor did it and said, I don't know, but I mean, your disease is very severe. You need a lung transplant. We now have the ability to do it. And they did it, and they learned, and he was part of his experience became part of the research as well, that it's not a factor type of deal, but it's the tissue itself. And so if you get non-CF lungs, your lungs are not going to have CF. In 1989, the gene was discovered. This is exactly 40 years after the genetic pattern was described and hundreds of years after CF was first described. And again, most people probably know some about this story. There were three collaborative researchers, Choi, Reardon, and Collins, Francis Collins. Francis Collins is probably the one who was closest to our CF community because he was, and Francis Collins is now director of the National Institutes of Health and exceedingly famous and prominent and so on. But during these years, his research was very heavily related to cystic fibrosis, and he was the keynote speaker for the NACF each year. Absolutely wonderful speaker, wonderful teacher, very optimistic and inspirational. And he sings and plays the guitar, and came out on the stage and sang and played the guitar, and just the coolest guy, and humorous. And so I don't think I ever met him or shook his hand, but I feel like I kind of know him. And so again, the personal stories of going to CF are just wonderful. Now, I almost forgot the deal about Woody Guthrie. Arlington. So, what these three people were doing at the time the technology that they had when they discovered the gene and the chromosome that it was on, and then where the gene was on the chromosome. They were developing some technologies to find that, and it was very, very difficult to find these genes. I don't have the knowledge to know why, but it was extremely difficult, and it was likened to finding a needle in a haystack, or one piece of hay in a haystack, which is, I guess, even harder than finding a needle. And it could have taken decades beyond this, but there was a lucky kind of thing. They started fooling around with Huntington's chorea gene a little bit, and they couldn't find it, it was just impossible to find, and they were looking for genes that were close to it. They kind of honed in on it, but they couldn't find it. And then somebody discovered a family grouping of Huntington's chorea somewhere in South America in the Andes, way isolated, and out from civilization. And there was a lot of intermarriage, so there was a lot of consanguinity, that's what we say in medicine, except I can't even say it apparently. They traveled down, got blood samples and so on, and looked at this pedigree of people with Huntington's chorea, and somehow that allowed them to make a huge jump, not only to find the gene for Huntington's chorea, but also they could then take that technology, and the very next disease they turned it to was the cystic fibrosis gene, and very rapidly, after a couple of years or whatever, after the Huntington's discovery, they were able to discover this gene. So, just again, very cool stories. In late 1989, within the same year, I guess the point of this is, within the same year that they discovered the gene, actual gene therapy was done in cystic fibrosis, at first in the test tube, and then in real human beings. And so in some senses, when people say, well, is gene therapy ready yet? In some senses, gene therapy for CF, curative, in a sense, curative gene therapy, has been done for all these many years. And I can't subtract it in my head, so I don't know how many years ago 89 was from now, but however many it was. But as I think a lot of people know, they ran into all sorts of roadblocks, and now they're trying to undo those roadblocks and really get it to work so that we really can cure CF. But it was actually done back then. So then, okay, now our current era, the 20-teens or whatever you would call it, we're getting fancier and fancier about the gene and what to do about it. So in 2012, Kaleido came out. This was exactly 406 years after the Spanish professor described his finger-licking test. And I was able to prescribe Kaleido for a patient who we all know and love. And it's not really a cure, but Kaleido is so amazingly effective, I think people know the story, that it's nearly a cure. I mean, it just turns things around so dramatically. And then in 2015, Orkambi for other genetic mutations came out on the market. In 2016, who knows, except I'm going to now switch gears. But so that's my little history of cystic fibrosis, and I would love people to tell me theirs, because again, I think everybody's story is really important, and I just think it's really exciting that personal stories behind it. And I'm sure every area of medicine is like that. It's not just scientific discoveries and people just trying to either make money or make a name for themselves. There's personal stories always, and that's what really makes medicine so wonderful. Okay, so now we're going to switch to what's new, and there's a lot of information and not a lot of time, so I'm just going to concentrate on a couple of things, and I have a bunch of slides I'm going to flip through and not even look at. But I do feel it's important, and what should I put till 12:10, 12:15, 12:10 or something like that. Okay. So who knows how far I'll get? Maybe to this slide. Anyway, this is a slide that anybody who's come to that I think has seen this before. I really believe that even without, if you don't have any scientific background at all, it really doesn't make a heck of a lot of sense to talk about what's new in terms of treatments without knowing what the disease is all about. I mean, what, otherwise just names of medicine. So I always like to go through this a little bit, whether I'm talking to medical students or other doctors or people that have no medical background at all. So cystic fibrosis, thanks to that, 400 years of discoveries, we now kind of know so much about it, and we know how it occurs. So cystic fibrosis is a genetic condition. I already described the gene that is autosomal recessive. Both parents have to carry it. And what the gene does is to make, again, all genes make products, make parts of cells or types of tissue, and the cystic fibrosis gene makes a particular chloride channel, and I'll mention that in a minute. Now, one important thing, and Rebecca knows all this stuff so well, and she just throws around these terms like, well, everybody knows that. But she mentioned in passing, and some of you probably picked it up and some didn't, messenger RNA. You'll heard her say that. But what's the deal with RNA? We know about DNA, that's Watson and Crick and the snakes and all that. But the fancier part, and I should update this slide someday, except I'm too lazy, is that the DNA is a blueprint, but it doesn't directly lead to the making of it. And let's just talk architectural, blueprint of your house. You can't just take that. It's not a usable blueprint. And what has to happen is that DNA gets translated into RNA. So it's like a copy, in a sense, or a mirror image copy of what's in the DNA. And the RNA is actually capable of then being used as the working blueprint to make the house. And we've spent so much time, scientists in the last many years have spent so much time trying to fix the DNA because that's where the basic defect is. And they may still do it. It was done in 1989, but not in a practical way. And that may well still come, and it may come fast. But in case it doesn't, another approach, and this is a newer approach and very exciting right now, is, well, if you can't fix the DNA, let the DNA make the RNA, that's your working blueprint, and then fix the RNA so that you make the right kind of house and not the wrong kind of house. So that's what she was talking about. So that's the step in between the first step and the second step. And then specifically, when you make this chloride channel that is not normal, then you don't get chloride and sodium going through a probe. I'll go through all that. But the result of that is stuff that you all do know, and that is that you end up with dried thickened secretions in the bronchial tubes, elsewhere in the body as well, such as the liver ducts, but we focus so much time on the lungs. That causes obstruction of the bronchial tubes. The bronchial tubes get infected, and you end up with thickened secretion. And there's the picture there on the right, pointer, but the picture of a bronchial tube. That should be clear. That should be white in it, but instead there's a bunch of gunk in it because there's thickened secretions, there's infection, and there's a bunch of things that your body has made to fight infection. They're all gunked up in there, and they cause cystic fibrosis. Okay, so and I can't remember. Just kind of go through this part, the bottom part down here, bottom three steps, also have been described as a vicious cycle. And what happens is that with CF, you have thickened secretions to begin with. Everybody knows that. And the thickened secretions get infected. They trap bacteria. They get infected. The body fights the infection with a very, very complicated process called inflammation. And that's important for killing the bacteria. All these antibodies and T cells and a bunch of proteins and a bunch of different stuff that fights infection. But in the process of that, the inflammation itself, or the fighting, the part that's fighting infection, creates even more thickening. It creates products that thicken the secretions even more, and it also creates products that damage lung tissue. So it can damage bacteria, but can also damage lung tissue. They call that innocent bystander damage. So anyway, you get this vicious cycle: thick secretions, infection, inflammation, obstruction of the airways, more thickening, more infection, more inflammation, and so on and so forth. And there's a lot of esoteric research now, esoteric in a good way. I mean, it's esoteric because it's hard to describe and hard to summarize, but it's actually very important. A lot of discussion about which comes first in this process, and I'm not going to go into that at all, but if they discover exactly which of these things comes first, that may be another whole line of research for development of tools that might be helpful in treatment. Okay, so everybody get me, I'm not going to go through any of this stuff. And here, so here is one way of depicting, and what I'm going to get to in just a few minutes is Kendra gave me, fortunately, as I was trying to figure out what I was going to say, some wonderful little videos that we're going to queue up here in about 5 or 10 minutes, that once I describe this, I think the videos will kind of finish it off. It's hard to watch the videos, they're very fast, but they will basically show the chloride abnormality, but you kind of have to go through some first. So what we're talking about here is, let's just talk about bronchial tube. Again, we could be talking about pancreatic ducts or liver ducts or whatever, but to simplify it, and because it's so important, we're going to talk about lungs. So in bronchial tubes, there's a cell, and the top, and again, we don't have a pointer, but I think I can describe it. So the top is actually where your bronchial tube is. So imagine a big tube along there, and then that complicated structure there is a cell that lines the bronchial tube. And I don't know if I have a different picture here or not. No, okay. But there's the inside of the cell that is below that thing. So that's the cell surface. Above it is the bronchial tube itself. Okay, and that I'm sort of colorblind. I don't know if that's gold or orange or what color it is. The CFTR, that's a chloride channel, and that's at the edge of the cell. So inside the cell that is lining the bronchial tube, there is chloride that needs to, in an appropriate situation, in a non-CF situation, chloride travels through. It's a channel. It travels through this channel, gets outside into the bronchial tube itself. And the chloride, when chloride gets out there, there's appropriate balance, and water can, it's just like, let me make it simple. It's obviously it's not simple, but you know, when you pour salt on a slug, it pulls the water out and kills the slug. Okay, so you want to have salt out there in the bronchial tube so the water can go out there, and water makes nice thin secretions that are normal airway secretions and helps to keep airways clear of bacteria and so on. In cystic fibrosis, this chloride channel, in one way or another, is having problems and doesn't work or may not even be there, and so chloride gets stuck inside the cell, and water gets pulled inside the cell, so you have a nice, hydrated, wet cell, but you have dry secretions out in the bronchial tubes, and that's the start of the problem. In addition to that, there's totally different channels that sodium goes through, Na. And there's kind of a double whammy that's a very complicated interaction, but basically when you have cystic fibrosis and chloride gets stuck inside your cells, extra sodium gets pulled inside the cell too. So now you have both sodium and chloride that's pulling water into the cell, and you get even drier secretions. So that's kind of what we're stuck with. Now, this slide does show that there are other kinds of chloride channels as well as the cystic fibrosis chloride channel. And to some extent, that kind of chloride channel can make up for an abnormal one, but in general, not well enough. So that's the abnormality we're talking about. Now, the other thing, and this looks like a very complicated slide, but I think it's getting more and more familiar to you, or maybe it's familiar to everybody here. I'll go through it briefly. When they discovered the mutation for cystic fibrosis in 1989, they were very excited, and then pretty soon they found another one, and then pretty soon they found another one, and all of a sudden, although it was fascinating and exciting, it also got to be a little bit like, oh geez, you know, it's like, this is way too complicated. We just thought there was a CF mutation, and we were going to work on the gene to fix it. Turns out there's about 2,000 different mutations that can occur on the DNA to make cystic fibrosis. And that creates a lot of logistic difficulties in terms of how do we approach it so that we can do some various things to treat fix it. One of the things they were able to do, though, after a few years, even though there's 2,000 different mutations, they were able to divide them into 5 different types. And that's what's depicted here. And I just go through it briefly. So in the normal situation, imagine at the bottom, that's where your DNA is. That's kind of way deep in the cell. Okay? And the DNA makes the messenger RNA. The RNA makes the protein, which is a chloride channel. Chloride channel gets on up to the edge of the cell. Chloride goes through it nicely. Water can pull through because chloride is, and you have nice moist secretions out in the bronchial tube, which is those dots on white on the top. Okay, but when you have a cystic fibrosis mutation, various things happen to goof up the chloride channel. And the class 1 mutations are ones that we used to call them just stop mutations. I think they're called nonsense mutations now. But anyway, basically what happens with that is the DNA has such a weird abnormality on it that the RNA doesn't even, there's no blueprint basically. You start with the DNA blueprint, but you don't get a good blueprint. You don't make any chloride channel at all. And it's as if, you just don't. So when you go up and you look at the top of the cell where chloride should be able to go through this and out into the bronchial tube, there's no channel. Class 2, similar to that, and this is the delta F508, the most common one. And this is, you make the blueprint makes an RNA, and there's not a stop, so the whole full working blueprint is made, and an actual protein is made. So far, but that is not a normal house, it's an abnormal house. And the house is recognized by inner workings of the cell as being abnormal enough that they say, well, there's workings there, they say, well, this shouldn't be here, this is abnormal, we don't want this, maybe it's going to be cancer or something like that. And it destroys it so that it never gets up to where it needs to be a chloride channel. So that's the class 2. Class 3, the 551D, a protein is made, a channel is made. It looks like a pretty normal house, so it escapes through the inner workings of the cell, gets up to where it should be, but it's kind of a closed channel, and chloride can't go through. Class 4 is similar to class 3. There's something wrong with how stuff goes through it and how it's not being opened at the right time and so on. And in class 5, the channels are there. They, I think, work fairly well, maybe not as well as they should, but there's not as many, and so they need to pump out more, and they're not doing it. Okay, so all this stuff sounds very esoteric, but as we know, it's not esoteric at all because scientists are pushing out research and actually pushing out drugs that will address these different things. So, with that in mind, I think what I'd like to do, well, I'm just going to mention a couple of things. So going back to when I give this lecture, and I don't do the history and so on, I give it to medical students or so on. What I usually do is go through this whole thing, and then I talk about things that we can do now or things we can do in the future to treat all these aspects. How can we treat the lung damage that occurs? How can we treat inflammation? How can we treat infection? But again, we don't have time, and I wasn't planning to do that anyway today, because the real excitement is the what we call gene modifier therapy, or these drugs that address the abnormality of the gene. I did want to mention just 2 things in regard to other aspects. One is, if you have severe enough lung damage, bronchiectasis, eventually that's going to get to the point where a lung transplant may need to be considered because the lungs just aren't functioning well enough to sustain life. And we have had, and I was, last night, I think this number's right. Anyway, in our clinic, we've had 15 lung transplants through the years. The long-term survival for lung transplantation with cystic fibrosis is a 5-year survival of about 50%. And our figures, I think, match that pretty well. But the exciting thing is we've had 2 lung transplants in the last year. And so we we all hope in cystic fibrosis that eventually the cure will be here and be able to be started early enough in life that we'll never have to think about lung transplants. But some patients who have advanced lung disease, it's still something we think about, and it's something that we handle through this clinic, but of course we don't do lung transplants. And then the only other thing I wanted to mention before talking about the gene therapies is antibiotics. And as most people know, there are a variety of different kinds of bacteria that infect the lungs of cystic fibrosis. They're generally very different bacteria than infect lungs of other people who have other kinds of lung diseases. And in particular, we deal with a couple of very difficult ones. One is Pseudomonas, and Pseudomonas is one of the reasons it's so difficult to treat is there are very few oral antibiotics that are effective for Pseudomonas. So in the old days, that either meant that you had to use an oral antibiotic, or if you're sick enough, you have to do IV antibiotics, and those are the only two choices. Then along came inhaled antibiotics. Toby came along years ago, and one of the big advances now is we're waiting with bated breath for additional inhaled antibiotics for a couple of reasons. One is because the bacteria, of course, become resistant to the particular antibiotic that is introduced to over and over and over again, can become resistant. So we want different ones to be able to use, and we can tailor it to the particular bacterial resistance pattern that a patient has. And we also like to do the rotation. If you hit a bacteria with one antibiotic for a while and then another antibiotic for a while, in many ways that can be more effective, and it can also work towards preventing resistance to the antibiotic. So we're waiting for, and I have a slide at the end that will show some of these. Okay, so that's all I was going to say at this moment. Now, Kendra, can we put up a little movie that now hopefully will make some sense and show the idea of what's actually sort of in 3D, what's going on with inside the cell with the chloride channel, and can lead to discoveries of different drugs that are effective.
And I'm just going to say, if you're watching virtually, just make sure your mic is muted, please.
What else?
You get to hear everything that you say.
I think so. Yeah. So.
Cilia move rhythmically within a surface liquid, upon which floats a thin coat of mucus.
Start it again. Just one more try.
The airway lumen is lined with ciliated epithelial cells. The cilia move rhythmically within a surface liquid, upon which floats a thin coat of mucus. Inhaled bacteria become trapped in this mucus layer, and the beating epithelial cilia then propel the surface liquid, mucus, and embedded bacteria onto the lungs. This is known as mucociliary clearance and is the primary protection mechanism for the lungs. The CFTR gene encodes a chloride channel that resides on the surface of ciliated epithelial cells. The CFTR channel secretes chloride into the airway lumen. Additionally, it regulates sodium intake via the epithelial sodium channel, or ENaC. These processes help to maintain the correct volume of airway surface liquid. This in turn promotes optimal cilia function and mucociliary clearance. Cystic fibrosis occurs when there are two mutated copies of the CFTR gene, which is located on the long arm of chromosome 7. Variations of these mutations are identified by classes. The most common CFTR mutation is F508del, which is a class 2 mutation. CFTR protein is produced, however, is not processed properly and does not reach the cell surface. Lack of CFTR at the cell surface means there is no chloride transport out of epithelial cells. In addition, ENaC regulation is lost, resulting in excessive sodium absorption. This leads to dehydrated airway secretions, impaired mucociliary clearance, and chronic bacterial infection. A corrector molecule such as BX809 could potentially facilitate movement of F508del protein to the cell surface. Additional treatment with a potentiator, such as ivacaftor, could then activate these F508del CFTR channels.
And that's Orkambi.
No protein is transcribed by the ribosome with class 1 mutations such as W1282X, where a stop codon is inserted into the CFTR coding sequence. RNA is transcribed, but no full-length CFTR is produced. Clinical symptoms are similar in individuals with either a class 1 or class 2 mutation. Drugs such as adaluran may allow ribosomes to read through these stop codons, thereby potentially allowing full-length CFTR protein to be produced. A class 3 mutation such as G551D produces a CFTR protein which is processed properly and reaches the cell surface. However, it is not functional and does not transport chloride. This has a similar effect on mucociliary clearance as seen in class 1 and class 2 mutations. The gating defect found in G551D CFTR protein can be overcome by ivacaftor, leading to increased chloride secretion and clinical benefits.
And it's Kalydeco.
The R117H mutation with a 5T variant in intron 8 is an example of a class 4 mutation. This mutation results in the CFTR protein that is produced and makes it to the cell surface, but has decreased chloride conductance. This change in conductance is not enough to cause cystic fibrosis symptoms unless the amount of R117H CFTR that reaches the cell surface is diminished. This is where the 5T variant comes in. It decreases the amount of R117H CFTR that reaches the epithelial surface. However, there is still some residual chloride transport, so that symptoms are typically milder. Class 5 mutations such as 3949 plus 10KB C to T result in a splicing variant that leads to two types of mRNA. One mRNA produces a normal functioning CFTR channel that reaches the cell surface, while the other mRNA doesn't encode a functional protein. As with class 4 mutations, the resultant residual chloride transport in class 5 mutations typically leads to milder symptoms. Since some functional CFTR reaches the cell surface in both class 4 and class 5 mutations, a potentiator such as ivacaftor may provide clinical benefits.
Thank you. Let's go to the last slide. It's the drug pipeline. So I think those are really cool movies. I think it kind of puts it all together. And the last slide I'm going to put up is a very daunting slide that is called the research pipeline for cystic fibrosis. And it was a whole bunch of drugs that are being worked on, some of them almost ready, some of them very early research. And I'm not going to go through them basically, partly because I have very little knowledge about some of them. But just the purpose of the slide is two. One is to be inspirational. There's a lot going on out here. Well, there's three purposes. One is to be inspirational. The second is to emphasize that even though the gene modifiers and gene therapy are the exciting things which we're getting to take advantage of now and are hoping will cure cystic fibrosis, it's still important to be working on new antibiotics and new ways of damping lung tissue and whatnot. So there's a whole bunch of things that are, and it's just, as Rebecca said, there's so many trials going on, kind of running out of patients who can participate in the trials. And that's an embarrassment of riches. Oh, okay. Well, even if you don't get to, so let me, as I say, I don't know about most of them, but there are a whole bunch of drugs. We have Kalydeco now, we have Orkambi now. You saw how they can work to fix what's going on inside the cell. There are other molecules that are similar to those that may or may not have an advantage over what we have now. The drug trial we have going on now that we're participating in here is kind of a variation of Orkambi. It's a different molecule that may, we hope, be more effective than Orkambi. And okay, so that's the 1, 2, 3, the D661 ivacaftor, and that's the phase 3 trial that's going on right now in our clinic and others. And too early to say, but the pilot studies indicate that will likely be a more effective drug than Orkambi. So everybody's on Orkambi, gets some benefit out of it, and then in a few years, Orkambi may kind of disappear, and that new drug or something like that. Some of these others are similar variations on a theme that may have an advantage in one way or another. One that is interesting, it's a little bit different, is the P1037 down in the second set of bars. And that actually has nothing to do with the chloride channel. Remember, the defect is in the chloride channel, so not enough chloride gets out of the cell, but at the same time, too much sodium goes into the cell in regular CF. And this is a drug which inhibits sodium from going into the cell. So it's a different way of looking at